As we come down towards the end of our Calculus 1 course, we want to look today at two things. First of all, integration involving natural log functions. Now we know that the derivative of the natural log of x is 1 over x. Therefore, the integral, the antiderivative of 1 over x dx would be the natural log. And because logs can only work on positive numbers, you need the absolute value plus c. And the derivative of the natural log of u is u prime over u. So the integral of du over u, 1 over u du, would be the natural log of the absolute value of u plus c. And the real key is recognizing. I've got a 2. 2's are coefficients. So if I take it out, rewrite, I get 1 over x dx, and that looks exactly like this rule. So it's 2 the natural log of the absolute value of x plus c. The 2 becomes an exponent going in, and x squared is always positive, so we get rid of the absolute value. We have that. We don't have a quotient rule. So when I see a quotient, one of the things I might start thinking about is it related to natural log? Because natural log is a quotient. Well, the problem is this is too much down here, so we let the too much be u. The problem is almost always u. So u is 4x minus 1. The derivative of that is 4 dx. So in place of 4x minus 1, we can put u. In place of dx, we can put du over 4, or 1/4 du. And now this matches exactly. And so we have 1/4 the natural log of the absolute value of u plus c. U was 4x minus 1, so this gives me 1/4 the natural log of 4x minus 1 plus c. And so we have a way of using natural log, or getting natural log. Find the area. Back in the beginning of this unit, we said that the area was the integral. Here's the function. The area under the curve was the integral from beginning to end of our region, from 0 to 3, of the function x over x squared plus 1 dx. So we can evaluate that integral, I can find the area. Now again, we do not have a quotient rule. So when I see a quotient, I need to think a little bit about logs. So that a proper fraction, so I can do that nicely. And I've got an x dx, which is related to the derivative of x squared. So if I let u be the denominator, x squared plus 1, then u prime is 2x dx. So in place of, so x squared plus 1, I would need a 2x to have the right du. So I can put a 2 there, so I undo it. So now this is du over u, which is the natural log. Since x squared plus 1 is always positive, I don't need absolute value there. So I have 1/2. Now I put 3 in and 0 in, and the natural log of 1 is 0. So I have 1/2 the natural log of 10, or approximately 1.151. So recognizing becomes the big key. Here is a fraction. We do not have a fraction rule. We do not have a quotient rule. But notice it's a proper fraction. X squared, x cubed. So I can think about this, recognizing the derivative of x cubed plus x is 3x squared plus 1. So this is du over u, which is the natural log, the absolute value of x cubed plus x plus c. Or secant squared over tangent dx. I do not have a quotient rule, especially for trig, but I got to remember that the derivative of the tangent is secant squared. So this is du over u. So I have the natural log of the absolute value of the tangent plus c. And that's the approach that we use to find these types of integrals. So basically, integration is looking around and saying, okay, I got the answer, what's the question? Right? Derivatives, we've got the question, I'm just going to go right to the answer by doing the rules. But integration, you have to think backwards. So first of all, we need to learn or understand or know where to find basic lists of integration formulas. You need to have that with you. Then find an integration formula that resembles all or part. And then by trial and error, pick a U. Sometimes it works, sometimes it doesn't. And then use U substitution. When you can't find a U substitution that works, then try to play with the integrand. Trig identities, multiplication, division. Do things with it. Be creative. And then we can always know that we have the right answer by checking our result at the end. So if we had something like, here's a quotient. I do not have a quotient rule. And this is an improper fraction. The degree of the top and the bottom are the same. So back in pre-calc and earlier in this course, we talked about fixing improper fractions by long division. X goes into x squared once. Subtract x lesser degree than x squared, so that becomes the remainder over the quotient. So now we have that this integral is 1 plus x over x squared plus 1 dx. I know how to take the integral of 1. It's x. X is part of the derivative of x squared. We looked at that earlier. So I can do this guy, and I now have found the integral. I have now found the integral. So we need to look at that. There's a whole course called differential equations. That when you have a derivative equaling something, an equation involving a derivative, and you really do that by integrating. So if we want to find y, we got to get rid of dy, so we take the integral, we get y. The integral is 1 over x, the natural log of x dx. Now when I look at my rules, I look at all the rules I have, there is no rule that has a natural log in it. None of them, right? So if I let u be the natural log, right, du is 1 over x dx. So this is du over u. It's just du over u. So it's a natural log of u. So it's going to be the natural log of u, which was the natural log of x, plus c. And we have found the integral. We have found the integral. And we do that with trig, guys. We already know the derivative of the sine is the cosine, or the integral of the sine is minus cosine. And the integral of the cosine is sine. What about the integral of tangent? Don't have a rule. But trig tells me that tangent is sine over cosine. Fraction. So let u be cosine. Du would be minus sine. And I can find it. Or the secant. I don't have a rule for secant. But I do know the derivative of the secant, to get a du for the secant, I need a secant plus tangent. So I'm going to introduce secant plus tangent, but I just can't introduce it without changing the problem. But secant x plus tangent x over secant x plus tangent x, that's 1. So now I have secant squared x plus secant tangent x over secant plus tangent. So I let u be the problem, the denominator. Du, derivative of secant, is secant tangent. Derivative of tangent is secant squared, and that's what our numerator is. So this is just du over u. So it's a natural log of u. U was the secant plus tangent. And so we have a few more rules, a few more formulas to add to our result. Here they are. We already know that the integral of the sine is minus cosine. The integral of cosine is sine. We just found out that the integral of the tangent is minus the natural log of the cosine of u. The derivative of the secant is natural log of secant plus tangent. And then don't always forget to remember the plus c. And likewise, we can find these values. And we can end up then using them to evaluate. Here's the definite integral. It means the answer's a number, not plus c, a number. But I can't do it because I don't know how to do square root. But I should remember that tangent squared plus 1 is secant squared. So in place of the 1 plus tangent squared, I can substitute secant squared. The square root of secant squared is secant. I just found out that the secant is the natural log of the secant of x plus tangent of x from 0 to pi over 4. Secant of pi over 4, secant goes with cosine. Cosine of pi over 4 is the square root of 2 over 2, so this is 2 over the square root of 2, or square root of 2. Tangent of pi over 4 is 1. Put 0 in. The secant of 0, cosine of 0 is 1, so the secant of 0 is 1. Tangent of 0 is 0. Since the natural log of 1 is 0, the answer is the natural log of the square root of 2 plus 1, which is approximately 0.881. So some more rules of using integrals. We're going to look at one more set of things for the inverse functions. So start working on this as we begin to finish up the course.